So to repeat again, the spherical symmetry of the problem and the fact that if you go around phi by an angle 2 pi, you get back to the same point. That's the physics that dictates that this function is such that this quantum number m is quantized. It's quantized to be an integer. This gives you the angular dependence of your hydrogen atom wave function. Hi guys, so welcome back. Hope you're having a nice weekend. So let's start with lecture 11 and lecture 12, which I'll post sometime later. These two lectures, I would want to focus on the hydrogen atom problem in quantum mechanics. This is central. This is one of the epic successes of quantum mechanics in the 1920s. This really set quantum mechanics on firm footing. So we'll take some time and do them slowly and hope you enjoy the ride while we do it. So that's why I decided to break it into two lectures, and we'll have them one by one. So let's begin with, say, for example, let's begin with lecture 11 right now. So, yeah. Okay, so where were we? So we were trying to solve this Schrodinger equation for various potentials, and we have seen as just since it has been a while, at least I wrote the Schrodinger equation. Let me briefly go through it just very, very quickly. The Schrodinger equation is an equation of this kind where this is an operator and this size are called the, that's right, this one is time dependent Schrodinger, wave function. Oops. Right. So let's think about this. Let's do this very slowly, okay, so that we enjoy what we are doing. What is this object that I write here? This is called the Hamiltonian, and all your life we will get to hear it a gazillion times. What is a Hamiltonian? Essentially, if you have done a bit of classical mechanics, well, first and foremost, in classical mechanics, Hamiltonian is not an operator, it's a function, but all that aside, it's basically roughly energy, right? Rather, the eigen value of this operator is energy. In classical mechanics, this really is associated with energy. So from classical mechanics, again, just trying to connect with what you know, this H would then be, say, the kinetic energy plus the potential energy, right? This is the total energy of your system. So what is T? Well, in relativistic physics, this T is p squared by 2m. And V, you need to specify from outside what your potential is, but we will focus on non-autonomous systems in the sense that your potential just is not time dependent. We will do time dependent potentials probably later in perturbation theory, if you guys are interested. So yeah, so drop comments and let me know if you want to do a bit of perturbation theory later. So for the time being, this is just a function of x, this potential, and it's time independent, not time dependent, that is time independent. This is maybe a bit of physics. If your T is quadratic, in P, in the momentum, right? Okay. So this is your Hamiltonian, and we have seen what your P is. In quantum mechanics, we have defined P, or we have actually not defined, we have figured out your P is minus IH cross del del x, right? So certainly then, which implies P square, operator P square, would be h minus h square by del del x square. This we have seen before, right? Except that now You want to do a 3D problem. This is your first three-dimensional problem, because you have let me draw this for the time being. You have a three-dimensional spherically symmetric problem, actually, to be even more precise. So say this is your coordinate system, and since you're going to deal with say a hydrogen atom, for example. Eventually I want to solve this problem for a hydrogen atom. You know that the Coulomb potential is spherically symmetric, right? So the potential x is proportional to radial distance. This we know from classical mechanics, and this is also understandable, right? I mean, if you have an electron or a proton sitting here, you would imagine that your potential is actually just a function of this distance. This distance is what we call r in this notation. So let me draw the Cartesian coordinate system. Say this is your r, this is where your point sits. So this is a perpendicular onto the xy plane. This distance is r, and this is so this distance is called the phi. This is in this plane, okay? This is phi, this is r, and this is called the azimuthal angle, which I will call theta. Okay, so this is your three-dimensional space, the space of everyday life, right? Your space around you is three-dimensional. Why three-dimensional? Because you need three numbers, r, theta, phi, to specify a point. It could have been x, y, z also, right? But you need three of them. The important point being you need three of them. So this is a three-dimensional space. Why have I chosen the r, theta, phi coordinate? Because your potential, I mean, this is the adapted coordinate system for the problem, right? Because your potential is a function of r. The problem that you're trying to solve here, has a symmetry, that the potential is not a function of theta, is not a function of phi, it's just a function of r. So you would expect your solutions to have that symmetry, and therefore you have chosen this r, theta, phi coordinate. Good. Okay, this is a bit of physics. So where were we? Right. So in this 3D, I mean, we have seen this for the 1D systems that we have been solving till now. It's very natural what the 3D version of it would be, right? So the 3D version of it would be minus 8 square plus by 2m. In Cartesian coordinates, it would be dx square plus dy square plus dz square, right? What has happened? Nothing has happened other than the fact that you had a del del x here, which has gone to del del x, del del y, and del del z. So this is the most natural thing that you would have, right? In the xyz coordinates. But of course, we are not working in an xyz coordinate. We are working in the r, theta, phi coordinates. So of course, this operator would look a bit different, because they would be in terms of the del del r, the del del theta, and the del del phi. Okay, good. Right, so let's write the Schrodinger equation. Oh, by the way, this is also called, I think I have mentioned this sometime before, but let me just remind you that this operator is called the Laplacian. Again, the celebrated operator in physics, because all bosonic particles belong to the kernel of your Laplacian massless particles. But okay, good. So let's write what happened. So okay, so we are not done. We have written what p square by m is. So your Hamiltonian right now would simply be, can you tell me what it would be? Exactly, it would be 1 by 2m px square plus py square plus pz square plus whatever your potential is, which I have specified in this problem to be a function of just r, right? Okay, we know certain things as well from previous lectures. We know a few things that we will borrow. I don't like the color, so I'll change it back to black. Okay, from previous lectures, we know a few things. What do we know? That for the in going to the time independent Schrodinger equation, we choose an ansatz for the capital psi, which the time, a bit of notation. If I write an x bar, this means of all the coordinates, right? Just x, y, z or r, theta, phi. So it's like more than it. It might be more than one. That's what I mean. So this has, we know this, right? This was an ansatz that we had chosen, again x bar, because it's a 3D problem. And this was e to the power minus I by h cross en of t. And there was a label n here, right? So let me also have a label n here. And your full wave function time would be a sum over cn. Some cn's we had to find out. And this guy. Right? We have known this before. And for the quantum mechanical interpretation, we also know that these three are psi, sorry, no n here, xt what square. What was it? It's 1, right? Because why? Let's briefly recap again. Because this was the probability, and probability integrated over all space should give you 1. The particle is somewhere, right? So yeah. Okay, with these two things at hand, let's actually delve into the real problem. So claim 1. Let me give you some reference to derive this if you want. You can look at the book by Mary L. Boas or Arfken Weber. All these are locally available either in libraries, or you can easily buy them, or Benz. I personally definitely follow these two, and this one is, I feel, a bit easier than B and C. Here you can figure out from here, I'll not do it, but you can figure out how to go from the XYZ coordinate to the R theta phi coordinate that we need for our problem. I'll give you the answer. So this Laplacian that we had written before as simply del x square plus del y square plus del z square. This, in terms of the R theta phi coordinate, becomes a little messy. 1 by r square del r square by del r plus 1 by r square sine theta, sorry, del theta acting on sine theta d theta plus 1 by r square sine square theta del square del phi square. So a couple of pointers. Of course, you had the original Laplacian in terms of x, y, z. So also here, right? I mean, it is in terms of del L r, del L theta, and del phi. Okay, that hasn't changed. Of course, it has picked up some functions here, some ugly looking functions, and the reason is this this xyz coordinates is it's just a normalization issue that you have for the r theta phi coordinate. Both are orthogonal coordinate systems, in the sense that I mean, if you have if you have a unit vector along the x direction and a unit vector along the y direction, let me write it. For example, ex dot ey would be 0, as also er dot e theta would be 0, for example. So these are both orthogonal coordinate systems. Orthogonal coordinate systems. But xyz coordinate is just better normalized. So you don't have any funny functions sitting here and here and here. It's just that in the r theta phi coordinates, you would have some functions. And these are universals, okay? One way to also see it, for example, a volume element in the xyz coordinates is simply dx, dy, dz. However, the same in r theta phi coordinate actually has an r square sine theta. So this is really what is called a Jacobian of your system. This is called a Jacobian. For those who know, it's just these are additional information. For those who don't, this is called a Jacobian, and it's just telling you that the particular length elements are sort of different. Okay, that's what. Yeah. So the length element are particularly dr, r d theta, and r sine theta d phi. Okay, so the product of which gives you basically this r square sine square theta. R is r square and sine theta. So yeah. And of course, I'm being very sketchy here. The main place to study this from are these references. If you want the easier version, it's just this one, or you can also study from here. Okay, good. But these were just some asides. Right. Good. So let's proceed. Yeah, I wanna rub this. This was just some explanation. I don't need it. Okay. So this gives you your so what happens to your Schrodinger equation? Well, now you know what happens to your Schrodinger equation, right? Your Schrodinger equation is simply the time independent one is minus h square by 2m Laplacian, where this is the Laplacian. This is the form of the Laplacian we would use because of the particular symmetry of our problem in the r theta phi coordinate times psi plus. So this was t psi, right? Because p square, this was p square by 2m. So this is t plus v psi, but v is a function of just r is equal to e psi. And these equations we have seen multiple times. This is called eigen value of h, of the Hamiltonian of h. This is also the energy, hence the letter E. So, and the goal is to find out both this psi and this E. This E is unknown. You have to figure it out. Okay. And how do we do it? Well, we have again, the reason I'm doing the 3D problem now is because we have already some experience as to how to do it. So can you take a guess as to how we should proceed to solve this problem? Well, as I had mentioned in one of the lectures before, the first go-to thing that people do in trying to solve these differential equations is called the separation of variables. That may be consistent with the nomenclature of Griffiths. This was, what was it called? Right, separation of variables. Why? Because you see you have separated the r and the theta phi part. In your mind, do you have a question as to why is it that I have just separated the r part and the theta phi part? I mean, why not, for example? Okay, let's take our time and just, try and have some fun. Say some r tilde r theta. Why not this guy? I mean, what's wrong with this? Why is this not a good separation of variables, say? Do you have this question in your mind? If you do, you're thinking along the right lines. I want you to have this question in your mind. Let me tell you why this is not the case. Why this is, of course, that could have been the case, but that is not a sensible separation of variables. You see, again, you have to think about what problem you are trying to solve. The problem that you are trying to solve is you have a central nucleus and you have some electrons revolving around it, right? Well, clearly not at the center, somewhere here. So you imagine, as I had said, that this potential just depends on r. So it seems that for your problem, all these points are equivalent points, right? Because there is a radial symmetry in your problem. All these are seemingly equivalent points. Again, these are seemingly equivalent points, for example. Say, these points. Why? These are all equivalent points. Why? Well, because this is some other r prime. Of course, different from r, some other r prime. But the radial symmetry of the problem seems to dictate that these points are all equivalent. Right? Again, these points are all equivalent, for example. So that's why you have sort of broken it into an r part and remaining part. So that's why the separation of variables are in terms of r and theta phi. Okay? Just bearing in mind the symmetry of your problem, that's all. But that's a crucial input that you need to give from outside. You have to understand what problem you are trying to solve. That's sort of like what good physicists or what good mathematicians would do. Like they would also have some idea of the kind of problem that they are trying to solve. Okay, good. So let's plug this back into this equation that we wrote, and we get what we get. Well, what do we get? We get an ugly expression. But nevertheless, let's write this. R square tilde r plus r square sine theta tilde theta sine theta y prime. I'll also use prime sometimes because it's just a function of one variable. So prime means derivative. Just when if I get tired of writing r square sine square theta d2 phi d2. Oh, this is actually, you are right. Did you spot it? Actually, that's one place where I cannot use theta, because this is a function of both theta and phi. So this is with respect to theta. This one is with respect to phi. This is what you will get. So what happened for those who are joining late? Like, briefly tell you what happened. Well, you see, this we have separated this variable, and that's the whole point of this exercise. This r is now just a function of r, and whereas this y is just a function of theta and phi. So this derivative acting on r, this ddr that we had in this Laplacian here, this ddr, for example, it acts just on r, and this this y piece comes out. Likewise, for the del theta and the del phi part, this r part comes out because there is no theta or phi dependence on r. R doesn't have any theta or phi dependence, but your del theta and del phi acts on the y, the function y, right? That's what you get if you plug this back into this equation. So this is just the Laplacian part plus, plus v times psi, which is r of r times y of theta phi, gives you energy times r of r y of theta phi, right? What is that? Well, that is just this psi and this psi, because your psi is r and r times y. Okay, good. Do you remember what we do need to do next? Well, do you recall? If you don't recall, go through the previous lectures that we had, the times we discussed this together. The next step would be to divide everything by r and y, right? So that this r, for example, cancels and this y cancels, right? You divide everything by r and y. That's how you separate the variables. And once you separate the variables, you will be left with two equations. Let me write the two equations down. So equation 1 is 1 by r ttr. Now I'm using total derivative, not partial, because this is just a function of one variable. Vr minus e is a constant, of course, is equal to something, some constant, to the angular equation would be 1 by 1 sine theta del theta. This is partial. Do you know why this has to be partial? Think fast. Tell me why this has to be partial. Why did I write total derivative here but partial here? That's right. So this y has dependence both on theta and phi. So that this one is definitely partial. This one is definitely partial. Let's get theta del square y. Del phi square is equal to minus of the same constant, right? So that you add these two and you get a 0 on the right hand side. That reproduces this equation for you. This is one line, check, kindly do it. Okay, just divide everything by r and y, and note that a part of the part of the equation would just, this part of the equation would just involve r, that is this part, and the rest would involve just y and theta. And the argument that we discussed when we were doing it last time is that this is a function of r, this is a function of y and theta, and the only way the equation can be satisfied is if there are individually some constants. These constants we would, for the time being, no reason to there's no way of knowing why I'm doing this crazy thing, but let's call it r, L into L plus 1. Okay, we'll see later why this is a standard choice. Okay, so now we have two equations, and This equation, the radial equation, we will solve in lecture 12. And this equation, the angular equation, we'll solve today. This is lecture 11. Okay? Good. Okay, so let's try and solve this equation. So let's write it in a manner that I want to write it. How do I want to write this? Okay, let's write it in this manner. So let's multiply both sides by y. So, and you will be left with this equation, sine theta del theta times sine theta del y by del theta plus del square y by del phi square equal to minus L to L plus 1 sine square theta y. So what have I done? First, I have called this constant, as I mentioned, as L into L plus 1. And then I have multiplied everything by y and sine theta. Okay? Rather sine square theta. I have multiplied with y and sine square theta. So that this term is isolated and this gets multiplied by sine theta in the numerator because I'm multiplying by sine square theta. So that's what you get, sine theta times this plus this term gets isolated. And you see this, it's already quite nice, quite cute, right? Do you see why this is cute? I'll again give you 2 seconds to think about it. That's right. It seems to have separated again. Oops, this was not good enough. Yeah, I'm very particular about these things. Sorry. Do you see how to proceed next? That's right. That's right. So if you just multiply, if you just divide everything by, so this guy has separated out, right? This del y square phi square. How do I see that? Well, let's write this y theta phi as again a separation of variable. This is an ansatz. Say a capital theta of theta. This is called capital theta. And a capital phi of phi. These are very standard notations, so I don't want to mess it up. I want to keep them. And you plug them back, and you see immediately that this equation actually again gets separated into its variable forms. So it gives you a sine theta del theta, total derivative now because the variables are separated, and theta del theta del well, theta, there is only one function, right? Theta, capital theta is a function of theta. So this will give you plus L, oops, plus L into L plus 1 sine square theta plus 1 by phi do you see the magic? I hope you do. You see again that quite magically this part of the equation has nothing to do with theta, and this part of the equation has nothing to do with phi. That's the beauty of it, right? That's why you are doing separation of variables. You have literally separated the one equation to two different ones. So if this part has nothing to do with phi and this part has nothing to do with theta, the only way these two this equation can be satisfied, again, this is the crucial part, this is the logic, that's what you need to appreciate, is if they are individually a constant, right? If this part is individually a constant and this part is individually a constant, the same logic I applied here. that this part was just a function of r, and this part was a function of theta and phi. So individually, this part has to be a constant, and this part has to be a minus of that constant, so that if you add these two together, you get a 0 on the right hand side. That's the whole point, right? Okay, great. Then we are done. So let's do this. So this part phi double dot, because now I can do that because it's just a function of one variable. Let's call it. Oh, what does Griffiths call it? This is a very celebrated equation. Let's call this constant m square. Okay. Immediately, then this implies that this equation has to be what? And this equation has to be plus m square. Plus m square. So that this plus this gives you 0, which is this equation. Right. Okay, so let's call this equation A, and let's call this equation B. And we can easily solve equation A, right? At least it's just one variable, there's nothing there. So your phi A, your capital phi, the function of small phi, is simply some constant times e to the power im phi. Right? Right. How do I see that? Well, because if you take it, if you derivate this with respect to phi twice, then you get back equation A, and this is now, this notation is for integers. It means that this is an element of the set plus minus 1 plus minus 2 dot 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 up to infinity, but integers. Why integers? Well, this is again important. This is crucial. This is a bit of physics here, so pay attention. Go back to the original problem that you had. So this was your setup, right? This was your 3D setup. So your phi here denoted rotation in this plane. If I call this x and if I call this y, this phi was a rotation in this plane, right? So if I go around phi 2 pi and at an angle of 2 pi, I get back actually to the same point. Say I start from here, I go back to this point, and I come back to the same point. So the problem dictates, the physics of the problem dictates the simple fact that your capital phi, whatever function you have, should have this as your boundary condition. That is, if you rotate phi and you by 2 pi, you get back to the same point, so the function better be the same. This is dictated by the physics, and this leads to a quantization of your quantum number m here. Your m becomes quantized in this manner as I wrote. How do I see that? Because this quantization is satisfied by this boundary condition. Why? Because e to the power I m phi plus 2 pi, say phi plus 2, 2 pi is equal to e to the power I m phi is what this demands. E to the power I m phi cancels, and you are left with e to the power I m 2 pi must be equal to 1, which implies m is a function of c, right? This is what you get. So to repeat again, the spherical symmetry of the problem and the fact that if you go around phi by an angle 2 pi, you get back to the same point. That's the physics that dictates that this function is such that this quantum number m is quantized. It's quantized to be an integer. This is called the azimuthal quantum number, right? Okay, good. So So I've already found out one solution for you, which is this guy. This is one solution. And I'm left with finding out the capital theta. Okay, so let's figure out capital theta. So this equation is simply this B equation with the additional information that your M is quantized. And this is the equation you want to solve. And this is a standard equation in physics. This is called, the solution is called the associated Legendre polynomial. Okay, let me tell you what this has some A, this has some quantum number L and M, and a function of cos theta. So what happened? Well, let's see what happened. This has a discrete quantum number L, just as this function had a discrete quantum number M. Your phi was a solution for every integer value of M. So here M was a discrete quantum number here. So you have another discrete quantum number here, L. And this M is now a parameter of your theory because you, in your original differential equation, you had an M here. So this parameterizes this M. That's why there is an M here. Okay. And if you want a closed form expression, this PLM is known explicitly. This is this guy, 1 minus x square times mod M by 2 TDX to the power mod M y mod times PLX. These PLXs are called the Legendre polynomials. And the PLX are given by there is a normalization times TDX to the power L acting on x square minus 1 to the power L. Right? To actually derive these, you would again want to go back to the references that I mentioned here, which are, it has been derived in these books. For example, you could look at these books to actually derive this solution. These are this is a very standard differential equation in physics. Very standard. Okay. So one thing you immediately notice, maybe I will point it out, and for those who know, you know. So you see from this this expression for the associated Legendre polynomial, if your M, okay, first question, I had asked this question while I was writing this, you need a mod here, right? Because I had written that your M is actually plus minus, it's integer. So of course, ddx to the power minus 2 doesn't make sense, right? So this is a positive number. This is also a positive number. Hence, you have this mod. And secondly, I wanted to point out that if your mod is greater than L, then PLM x is 0, right? Why? Well, this is a polynomial. This is a function of x to the power L, right? You cannot have more than L derivatives here. So this is 0. This is 0.1 and 0.2 for every L, M runs from minus L plus 1 L minus 1 L. That is 2L plus 1 degenerate. Both of these facts are actually quite important. Both of these facts tell you that your spin angular momentum cannot be greater than your orbital angular momentum. This L is called an orbital angular momentum. This is called a spin angular momentum. And it also tells you that your spin angular momentum are 2L plus 1 degenerate. That is, fix a value of L, it has 2L plus 1 different values. So both of these facts are actually important, and once you later study hydrogen atoms or chemistry later, you will see both of these facts actually make an appearance. These would be the spin angular momentums, and these would be the orbital angular momentums for you. And this L equal to 1, 2, 3, etc. They would be classified as S, P, D, F, etc., in chemistry. Okay, but that's not important for the time being. I just wanted to point these two things out. So I have then figured out the full solution for theta phi as some constant times e to the power plm of cos theta times e to the power I m phi, where now m belongs to the set and L is the set 0, 1, 2 up to infinity. So this is the angular part of your hydrogen atom wave function. This gives you the angular dependence of your hydrogen atom wave function. In lecture 12, which will be in next class, we will now solve the radial equation. You might have wondered, nowhere did I till now need this Vr equal to something. Of course, the hydrogen atom has a potential, right? I mean, you have a Coulomb potential, you have some nucleus sitting here, and you would have some electric field around it. So this has some potential. So nowhere did we need it till now, of course, because we have not solved the radial equation. And in the next class, we will solve the radial equation together. Okay, in lecture 12. Okay, I will stop here. So if this was helpful, feel free to comment or feel free to share it with your friends, and kindly like and subscribe. It helps me teach. Thank you. See you next week.